Alright, so today we're going to be talking about integrals and how they can be used to find areas in various applications. So, areas in the plane. So we already kind of know that when we take, let's say, the integral of a function f of x from like a to b with respect to this variable d of x, we know that this is essentially us having some function f of x, and if this is a and this is b, what we're doing is um, we're taking a rectangular slice at each value of x between a to b, and we're just adding up that slice area. And when we add up all of these slice areas, what we get is this integral, and that turns out to be the signed area between the interval of a to b, right? So, and this dx over here, that tells us that because x is the variable with which like respect to we're finding the area, that just tells us that that acts as our width. If we were finding the area of like a function with respect to y, for example, then what would happen is we're varying y and then we're finding out like vertical strips. So knowing that information, let's look through different applications of when we would want to find out areas in a plane, and let's see how we can use integrals to find out the areas in all of those cases. So the first one is area between curves, and what this means is, let's say we have two curves, so I'll just call this curve A, and then curve A, and then over here we have some curve B, and we want to find out the area between these two curves, and let's just say that this is the interval we're worried about right now. And it turns out that if I call this upper curve a f of x and this lower curve g of x, the area between a and b is simply the integral from a to b of f of x minus g of x times dx. Now, logically, this makes sense, right? Because with the rules of definite integrals, we can split this up into a of b f of x dx minus g of x dx from the same interval. And we're essentially, what we're doing is we're taking the area under the curve of a of f of x, so like these sort of rectangles, and then we're subtracting off the area under the curve of g of x, so this green part in this case, and then what we're left over is just the area between f of x and g of x. Another way to look at it is when we do f of x minus g of x, we're forming a new function which at each point tells us the difference. And that's the same thing as for a particular x value, for example, in that interval, we're getting just this rectangle as our height, and then the dx remains the same. So we're essentially just summing up rectangles that represent the difference in these two areas. And so hopefully that like line of reasoning makes sense, because um, you're gonna have to use that line of reasoning often when you're dealt with different cases to find of like finding areas in the plane. So let's just start with our first example. This problem states that find the area between y is equal to secant squared x and y is equal to sine x from x is equal to 0 to x is equal to pi over 4. So in any of these problems, the first thing that you should probably do is find out how these functions are behaving in that interval, and that will help guide what integrals we have to take. So let me first grab sine x. So sine x, we'll call this pi over 4, we'll call this pi over 2. At pi over 2, it takes on the value of 1, and then we'll just have this arc right here. Now, secant squared x is just the same thing as 1 over cosine squared x. Cosine of 0 is 1, so we know that secant at this point is secant of x at 0 is simply 1 squared. cosine of pi over 4 is root 2 over 2. So root 2 divided by 2 squared is simply equal to 1 over 2 over 4, which is equal to 2. So at pi over 4, which is our other limit, we have it be we have secant squared take on the value of 2, and you probably can assume that the normal secant function looks like a parabola, and now we're just taking that parabola and squaring all the values, so now we're just going to get like a more steeper parabola. So that's what the function looks like, and we're interested in the area between these two curves. So this is y equals secant squared x, and this is y equals sine x. We're interested in the area between the curves on the interval of 0 to pi over 4. So we're interested in this green shaded region. Now, that green shaded region basically corresponds to the difference between that secant squared x term, secant squared x function right here, and then the sine x function. So if I were to represent this as an integral, I know my bounds are from 0 to pi over 4, and I know that the upper function is always secant squared x, and the lower function is always sine x, because that determines like the height, and the width is determined as I move in the x direction. So that's why I'm going to be doing it with respect to dx. And so now I have the integral I want to solve, and now the question just becomes of evaluating this integral. So the integral of secant squared x is just tan x. The integral of sine x is negative sine x is positive cosine x. So that's my integral, and I'm evaluating it between 0 and pi over 4. That becomes tan of pi over 4 minus, or plus cosine of pi over 4 minus tangent 0 plus cosine of 0. This is tangent pi over 4 is 1 plus root 2 over 2 minus 0 minus 1. So our answer is root 2 over 2, and that's the area. So root 2 over 2 units squared is the area. Let's continue on. I think the best way to get stronger at this notion is just do more problems. So let's do that. So problem 2. Find the area enclosed by the parabola y is equal to 2 minus x squared and y is equal to minus x. Area enclosed by these functions. So in this case, we're not given an interval. We're told that we have these two functions and we want to find the area enclosed between them. And that means we have to find the intersecting points between the functions, and that will help us determine the interval. So the first thing we have to do is find where these functions intersect. So to find that, we need to find out where 2 minus x squared is equal to minus x. Taking everything to one side, I have x squared minus x minus 2 is equal to 0. Factoring, I get x minus 2 times x plus 1 is equal to 0. That means my intersection points are at x equals 2 and x equals negative 1. And at these points, the corresponding y values are simply y is equal to negative 2 and y is equal to 1. Now, like I said, the next thing we should probably do is graph the function so we get a good idea of how everything looks like. Let's graph y equals negative x since that's simpler. And I know my interval is simply between x equals 2 and negative 1, so this should be a good enough interval. And negative 1, negative 2, 1, 2. So this is y. This is what x axis. And so y is equal to x is the straight line. Now let me graph the parabola. At x equals 0, it takes on value 2. I know that at x equals 1, it takes on value okay, this should be 2 by the way, and then this is oops, I messed up the axes. This should be 1, this should be 2. And so this is x, this is y. redrawing this line. This is y is equal to negative x. This is y is equal to negative x. And then drawing the parabola, takes on these values, and then at x equals 2, the y value for 2 minus x squared is simply negative 2. And then because it's symmetric across the y-axis, I can draw the other point. So my parabola looks something like this. And the question asks to find the area enclosed between the question asks to find the area enclosed between the parabola and the line, right? And so we can look at this graphically, that this enclosed area corresponds to this green portion. And therefore, what happens is our lower limit is similar to what we found algebraically at x equals negative 1. And our upper limit over here is x equals 2. And in both, or throughout this interval, the y or the parabola is above the line. And so we can solve this using just one integral with our area, with our strips of area being simply these rectangles that we have, and then the dx. So this is what our integral is finding. We're calculating this height of the rectangle, and then we're calculating dx, and the height is simply given by 2x 2 minus x squared minus x. And so our integral that we're solving for is simply between negative 1 and 2. And then, like I said, our height is the difference between the parabola and the line, which is 2 minus x squared minus x. And then because we're doing vertical, because our width is on the x-axis, we're doing our variable of integrations with respect to dx. The integral simplifies to 2 minus x squared plus x dx. Solving for the integral, we get 2x minus x cubed divided by 3 plus x squared divided by 2 on the interval of negative 1 to 2. Let me finish the rest over here. That is simply 2 times 2 minus 2 cubed divided by 3 plus 2 squared divided by 2 minus 2, and then plus 1/3 plus 1/2. So this is 4 minus 8 over 3 plus 2 minus 1/3 minus 1/2. So this becomes 8 minus 9 over 3 minus 1/2. So 5 minus 1/2, which is simply equal to 4.5, which is equal to 9 over 2. So that's the area enclosed by these two functions. All right, let's look at another example. Problem 3. Find the area enclosed by y is equal to 2 cosine of x and y is equal to x squared minus 1. So we want to find out where the intersection points are. So we have to do x squared minus 1 is equal to 2 cosine x. Over here, we cannot analytically use any tools to solve for the value of x. So the only way you can do this is by using a calculator, and when you graph it, you'd get that these two curves intersect at x is equal to plus or minus 1.265. So those are our bounds of integration, and let's draw a diagram to see what these two functions look like. So 2 cosine x takes on the value of 2. We know that pi over 2 is, pi is 3.14, and therefore pi over 2 is greater than this value. And so everything's going to be in between the first sort of arc of our cosine function. where at pi over 2 cosine becomes 0, and similarly at negative pi over 2 cosine 0. So this is 2 cosine x, and x squared minus 1 takes on the value of negative 1 when x is 0, and then increases from there like a parabola. And with the use of our calculator, we found out that the intersection points are indeed at these 2 points, and those are just 1.265, and then over here it's minus 1.265. And to find the area, to help settle our integral, we see that each strip is just the difference of the top curve minus this bottom curve. The top curve happens to be 2 cosine x, and the bottom is the x squared minus 1. And then our width is determined by dx. So therefore, our integration is with respect to x, and then the integrand is going to be the difference between the top and the bottom function, which means that our integral that will tell us the area is simply the integral between minus 1.265 and positive 1.265 of 2 cosine x minus x squared, and then minus 1 becomes plus 1 dx. If we were to evaluate this integral, we would get 2 sine x minus x cubed over 3 plus x between negative 265 and positive 1.265. And that would give us around 4.995 if you were to simplify this. But yeah, the biggest problem or the biggest challenge of any of these area problems is to figure out what our curves look like and to find out these strips that we're going to be summing up with the use of the integral. And once we find out these strips, we just plug it into our integral, and then we can solve the integral analytically. Now, yeah, continuing on, let's look at more types of area finding problems. So this is problem 4. Find the area. So find area in the first quadrant. Bounded above by square root of x, below by x-axis, and y is equal to x minus 2. So the first problem is just finding out what the region that we're trying to find the area of. So we're only dealing with the first quadrant, and our upper bound is the square root of x, but our lower bound differs depending on whether whichever one's higher, the x-axis or x minus 2. So let's try to draw out what these functions will look like. So we know square root of x sort of takes on this shape, and we know that the function x minus 2 takes on this shape where we have an intercept at minus 2, and then we are linearly growing from there. So we know that since the linear function grows faster than the square root function, there will be an intersection point somewhere in the positive or first quadrant. And so this area that we're worried about, which is bounded above by x squared or square root of x, is over here. Below by x-axis or x minus 2 is just simply this shaded in region right here. So that's the area we're trying to find. And in order to do this, we need to find some key points, particularly what this intersection point is and this point over here, because at that point, the lower function changes from being the x-axis to the line y equals x minus 2. And therefore, we will need to make 2 separate integrals to solve this problem. Because now these strips after the second intersection point become with respect to the difference of, or the height becomes the difference between the square root of x and x minus 2, and then over here the difference is just between square root of x and the x-axis, which is just y equals 0. So our height, like the functions with respect to our height, like the functions with which we find our height with respect to change at after this point, and therefore we will need two different integrals. But both integrals are also related to the variable x, as we can see here, since we're varying x and x serves as our width. So that's all the information this like drawing gave us. And so now let's look at the analytical tools that we need to find out particular points. So let's find out this intersection point over here. So square root of x is equal to x minus 2. I square both sides. I get x is equal to x squared minus 4x plus 4. Then x squared minus 5x plus 4 is equal to 0. Factoring, I get x minus 4 times x minus 1 is equal to 0. X is equal to 1. X is equal to 4. We know that one of these solutions will be a bad solution, and that's clearly x is equal to 1, because when x is equal to 1, y, which is equal to x minus 2, will be equal to negative 1, which is not equal to the square root of 1. So the only solution is x equals 4, and that corresponds to this intersection point. Now we have to find out what this point is, and that's simply the x-intercept of our function. So in this case, y is equal to 0. So 0 is equal to x minus 2, and therefore x is equal to 2. So this is at x equals 2. So we found out the two key points that we need, and now we set up our integrals to find the area. So the first integral is from 0 to 2, and like we said, the height that we're forming is between the x-axis and the square root of x function. So square root of x minus 0, since x-axis is just y equals 0, dx. And then the second region of the area corresponds to this portion after x equals 2. So that's just from 2 to this intersection point of x equals 4. And our area becomes, or like the difference in the height becomes square root of x minus 2. And then our width still remains dx. Now let's evaluate both of these equations. The integral of square root of x is simply x to the power of 3 over 2 times 2 over 3. Evaluated from 0 to 2. And then over here, we get 2 over 3 x to the power of 3 over 2 minus x squared divided by 2 plus 2x, evaluated from 2 to 4. This over here is simply 2 cubed, which is 8. Square root of that is the cube root of 8, or the square root of 8. So this is 2 over 3 times the square root of 8 plus this becomes 4 cubed, which is the same as, well, 4 to the power of 3 over 2 is the same as 2 to the power of 6 over 2, which is equal to 8. So plus 2 over 3 times 8 minus 16 over 2 plus 8 minus 2 over 3 times the cube root of, or square root of 8 minus 4 over 2, or well, plus 4 over 2, because this minus becomes plus, and then minus 4. Now simplifying everything, these two terms cancel out. This is 16 over 3, so 16 over 3. This is minus 8, this is plus 8, so that cancels out. 16 over 3 minus 2 is what we get, and then that simply becomes 10 over 3, which is the area. So thus far, we have basically seen that our variable of integration is x, and you might have been confused why I kept mentioning that dx is like what our width is, and that's because the variable of integration does not always have to be x. We can make our variable of integration y if it makes our cases to find the area easier. And to motivate that, consider if we had to find the area between like these two arbitrary functions. So this right function is like x is equal to f of y, for example, and then this is x is equal to g of y on the left. We wanted to find the area between these two curves. So essentially this shaded portion. Now, if we were to look at the variable of integration as x, we would be forming strips like these like horizontal or these vertical strips where our height now corresponds to like the same function itself. We don't get the nice property of like our height being the difference of two functions because both the top and the bottom correspond to the same function, and that happens because if we were taking the variable of integration to be x, we would be having to form that kind of height because our width is all along the x-axis, and so that would make finding this area much more difficult than if we changed our variable of integration to be y, right? So if we made a y, for example, and we looked at this like similar shaped function. Now if we've made our variable of integration y, that means that our width with which we're finding our area is simply on this y-axis, so it's dy. And now our height becomes again the difference of this right function, the left function. And I told you that the right function is just x equals f of y, and then the left function is like x equals g of y. And so the difference is simply f of y minus g of y. And now we can just do the same thing we've been doing before to find the area, but we integrate with respect to dy. And the bounds will just be from whatever this y value is at the bottom to this top y value. So y2 and y1. And notice how by just changing the variable of integration, or like just changing like which entails geometrically to like where the width of the strip becomes, by just changing that, we've made our problem much more simpler, and that will help us find the area much like faster and easier than before. So let's do some practice with this notion. And hopefully once we do the practice, you also see why sometimes you actually have to integrate with respect to y. So let's actually just use the old example that we had. So we had y is equal to x minus 2 before, and then y is equal to square root of x. We already know that this function looks like this, and minus 2, and then we had that. I told you that this intersects at x equals 4. This intersects at x equals 2. And before, we had to do two separate integrals to find the entire area of this region, because after x equals 2, the bottom function changes from y equals 0 to this function of y equals x minus 2. But notice how if we were to integrate with respect to y, we would not require two different integrals to find our area, because along this whole region, this whole region which we're concerned about, the right and left functions remain the same if we just look at everything with respect to y. So if we're changing our integration with respect to y, our width becomes dy, and our height at all of these regions, or all like our height is always the difference between the x value that x minus 2 takes on and the x value that square root of x takes on. So when we integrate with respect to y, the same area that we found last time can be done in one integral. So how do we do that? Well, we need everything with respect to y, since now we're going to be integrating with respect to y. So let's solve for y. So in this case, y plus 2 is equal to x. Well, I meant let's solve for x because we want what the x value here is and the x value at some arbitrary point here is, and we find the difference and multiply it by a dy. So this becomes x plus or y plus 2 is equal to x, and then this equation becomes y squared is equal to x. And we already know the intersection points from doing the same example before, but if we didn't do this example before and we had everything in terms of y, we could find out the y values where we get intersection points, and you'd get y plus 2 is equal to y squared, and you'd get y squared minus y minus 2 is equal to 0. That corresponds to y minus 2 times y plus 1 is equal to 0. Therefore, y is equal to 2, y is equal to negative 1. This is an extraneous solution because 1, the square root of x is not even defined there, and 2, because even if the square root of x was defined there, the last problem tells us we want the area in the first quadrant, so we are cutting off at y equals 0. So our lower bound is y equals 0, our upper bound is y equals 2, and that's our bounds of integration, so y equals 0, y equals 2. Our right function that forms the top of what we're trying to find the height of is this linear function, which is given by y plus 2, and the bottom function is simply the square root function, which is y squared, and times dy, which forms this width right here. Taking all of those infinitesimally small rectangles that we formed by doing this integrand and multiplying by dy gives us the total area and the interval of y equals 0 to y equals 2. And so over here, y is equal to 0. And so let's evaluate this integral. So y squared plus 2 divided by 2y minus y cubed divided by 3 from 0 to 2. This is simply equal to 4 divided by 2 plus 4 minus 8 over 3. So this is 6 minus 8 over 3. So this is equal to 10 over 3. And that is the same answer that we got before if you were to look back in the video. So clearly, like, you don't always have to integrate with respect to x. Sometimes you can do either one, but sometimes you have to do one or the other because it's almost impossible if we were to integrate with respect to one of them. And so the goal is like look at the graph and look at which axes we can use as the frame of reference, and sometimes using one will make your life much easier and make the problem much more simple. So let's continue on the same path, and there's going to be 2 more problems. We want to find the area, so this is problem 6. Find enclosed area between y is equal to x cubed and x is equal to y squared minus 2. So over here we have like a horizontally axis parabola, and then this is just our cubic function. So let's find out the intersection points. So I can rewrite this as cube root of y is equal to x, and so cube root of y is equal to x squared minus 2. And looking at this path, this seems like a harder path since I have to take the cube. So let's actually go back either way, I'll probably have to take the cube. If I were to well, yeah. And it turns out, actually, I don't think you can do this analytically. You'd have to use the calculator to find out where the points intersect, and you'd get that the points intersect at y is equal to -1 and y is equal to 1.793. Because well, okay, because yeah, the only other way would be like x squared of x plus 2 is equal to y, and then what you'd end up with is square root of x plus 2 is equal to x cubed. And then you'd have to take the square on both sides, and you'd get like an x to the 6th term. So the other way is like you get x plus 2 is equal to x to the 6th, and then you get x to the 6th minus x minus 2 is equal to 0. And you'd have to find the zeros of this function, and the only way you could like do that is find out, like, use the calculator, because yeah. So we get these limits through the calculator. Let's graph out what these functions look like. So the cube of x cubed, looks like this, and then so that is x cubed, and then we know that y squared minus 2, and then over here, actually, because this is y squared minus 2, this is actually like plus or minus square root of x plus 2. That looks like well, at -2 we have the value, it takes on value 0, and then it follows like the horizontal parabola. And we know that since the intersection points are y equals -1 and y equals 1.793, so this is y equals -1, and then this is y equals 1.793. So let's look at the choices we have. We could integrate with respect to dx, right? But when we do that, in this region, before x is equal to -1, we would be having vertical strips that have whose upper and lower function is both the same. And like I kind of motivated before, that makes finding the area much harder. So that kind of implies to us that we should probably be doing the integral with respect to y. And when we try to look at that strategy, it seems that in our whole interval between -1 and 1.793, we can form our strip in a way that the integrand will always be consistent. What I mean is the upper function that defines the higher x value is always this function, which is just the cube root of y is equal to x. And this lower function is always x is equal to y squared minus 2. And then this is dy. So integrating those like rectangles formed by the difference of these two functions on this interval will help get us the entire area. And so the integral that we need to solve for essentially becomes the integral from -1 to 1.793 of the cube root of y minus y squared plus 2 dy. Solving for this integral, we get y to the power of 4 over 3 times 3 over 4 minus y cubed over 3 plus 2y on the interval that I have established before, and that becomes about 4.215. So here we saw that we had both options, and we kind of saw what are the steps to evaluate which of these options are better for a particular problem. And so we learned all this like fancy integration tool, but at the end of the day, you're still finding out the area of a curve, right? And so whenever you're still finding out areas, and so using geometry is always a valid option as well. And if that makes cases easier, then that should be the tool that you should be using to find the area. So for example, let's say we had the curve square root of 4 minus x squared. We know that this is simply a semicircle between -2 and 2. And let's say we want to find the area bounded by y is equal to 4 minus x squared and y is equal to 0. So we're finding out essentially this area over here. We're finding out essentially um, this area over here. Therefore, our strips are just going to be, well, the best option is just having the width as dx, and then our height being the difference between 4 minus x, or yeah, 4 minus x squared minus 0. So the integral that you try to solve for is 4 minus x squared, the square root of that, dx, from negative 2 to 2. But we also know that this is a semicircle with radius 2. And so instead of solving this integral, which will probably take more time, you're prone to mistakes, we can simply apply what we know about semicircles. So this is a semicircle. And simply know, we use what we know about these, and we know that the area of a circle is pi r squared. And so half a circle is just pi r squared over 2. And we know the radius is 2, so we can easily just evaluate the the area being pi times 2 squared divided by 2, which is simply equal to 2 pi. So notice how, even though we have learned a lot of advanced tools of using integrals to find areas, at the end of the day, recall that you are still just finding the area, and integrals are just one way to help you find out the area. But going back to the basics of geometry that you've learned in so many years of school, that can also help us and save us from calculating complex integrals like this. Because this integral, to calculate it, you would need to do something called a trigonometric substitution, and that's just much more annoying than just simply applying this formula and finding out the area. So yeah, hopefully this made sense and you've been introduced to a lot of the ways and techniques to find areas and planes. And yeah, the common workflow is simply first find the region and then calculate key points, determine the variable with which we will integrate if we choose to integrate, and then finally evaluate the integral. Oh, there should be 4. And by key points, this is like intersection points and points that define the limits of the integral that we're trying to calculate.